So let's talk about the idea of entropy, because understanding spontaneity requires the understanding of entropy and understanding how other thermodynamic constants. So energy is easy, and enthalpy, H, is easy to understand. You know, you have a high energy state, a low energy state, we're going to see a decrease in energy and a release of that energy in order to get rid of it. So if we've changed energy, it releases it into the surroundings. Entropy is a little bit different because entropy is not like as static as kind of we understand it to be. So first of all, what is entropy? Entropy typically measures the randomness. People say randomness of a system, but really what it is it measures, or it is a measure of the distribution of heat and disorder of matter or heat. So that's ultimately what we see. It measures the randomness, or it measures the distribution of heat and disorder. So the more disordered something is, the more well distributed, the higher the entropy is going to be. So we're going to talk about this, but a gas has really high entropy because everything is disordered and all over the place. But a solid is really well formed, and therefore it has a very low entropy. And so the best way I can explain entropy is, imagine you're getting to school at the beginning of the year and you're living in a dorm room or living in some kind of room, apartment, whatever. You decide that's the year you're going to be really, you're going to be really good about keeping everything in order. And so you put all your clothes, your socks, everything in the dresser, everything's folded really neatly, it's closed up, and things are good to go. It is very well ordered. Over time, entropy increases because, you know, you get home from class, you throw something on the floor, you know, you don't fold it, it doesn't go back in the dresser. Ultimately, you are getting more and more messy. Entropy has won. Entropy is taking over, and entropy always wins, by the way. So everything is getting more and more disordered. So, okay, so you're in that state where everything is messy. So there is a term whenever you see a decrease in entropy. So your system has gone from ordered, low entropy, to very high entropy. Everything is all over your room. Okay, so finally you decide one day you want to ignore all your classes and you want to focus on getting your life in order, and you say, I'm just going to do laundry, I'm going to fold everything up and I'm going to put it in. So and you put everything back in the dresser how it originally was, and we're back to an ordered state. So we went from ordered to disordered, nature loves that, back to ordered. Okay, so by going through those transitions, something has happened. Entropy has decreased. Entropy can never decrease. And we're going to see this. The second law of thermodynamics says this. So ultimately, the question is what paid the entropy cost? If something becomes more ordered, something has to pay for that change, right? So the entropy of the universe is always going to be increasing. That's the second law of thermodynamics. I'm going to say it again in a little bit. What paid the entropy cost? So you went from ordered, your dresser was ordered, to disordered, and back to ordered. What paid the entropy cost? You paid the entropy cost. You put the biological effort in, and the time effort in, and all of the energy that you wasted is now released into the universe, and you have a more ordered system. So everything in the universe is like that. Everything in the universe is like your dresser. Everything is very ordered right now, but over time, everything is slowly going to equilibrium. Unfortunately, equilibrium is this well-distributed system where ultimately we're going to end up in this situation where every single molecule and bond is broken, and we have some amount of heat in the universe. And so that is what entropy is: disordered to ordered to disordered, but something always has to pay that cost. Entropy is a state function. So entropy delta S is always equal to final minus entropy initial. So we can measure entropy changes based on the system. Okay, so for a typical process, the delta S of a system is going to be based on two things: the Q, the heat of the reversible process typically, as well as divided by temperature, because temperature is going to massively affect entropy. So the unit we're going to have is joules typically for Q, and Kelvin. So joules per Kelvin is going to be our measure of entropy. By the way, this always occurs at a constant pressure. And our Q, again, just to simplify it so it's not heat, is usually equal to delta H because that's what it is. So mercury is liquid at room temperature. Its freezing point is negative 38.9 degrees. Its molar enthalpy of fusion. So molar enthalpy of fusion, heat change, is 2.29 kilojoules per mole. I have to put 2.29 kilojoules per mole in order to change it from fusion from solid to liquid. What is the entropy change when 50 grams freezes at its normal boiling point or normal freezing point? So I'm going to give you the value of this. So you can do this calculation. Your delta S of mercury is equal to Q over T. So I encourage you to figure out what Q equals delta H. So I encourage you to figure this out. You are going to end up with a numerical value of 2.44 joules per Kelvin. So I encourage you to do that one. Is it positive or negative? So that's the really important part here. You can do the calculation. I want you to do that. Is the entropy change positive or negative? Well, if it's freezing, okay, am I going from more ordered or disordered? So by going from liquid to solid, okay, it freezes. That means that is a negative entropy change. I'm going from disordered, liquid, to very ordered, which is solid. So it's going to be negative entropy change. Okay, some of those times we have to actually figure those out, much like delta H. Is energy leaving the system or entering the system? Well, the same thing here. Am I going from ordered to disordered or vice versa? So more ordered, becoming more ordered, it's going to become negative. What paid the entropy cost? Well, whatever is doing the freezing. So the freezer is doing the entropy cost in this case. Okay, so that brings us to the idea of the second law of thermodynamics. And I've already stated it. Here it goes again. Entropy of the universe is always increasing. And we could get into all of this. Ultimately, for a reversible process, delta S is equal to delta S of the system plus delta S of the surroundings, which is equal to 0. So for a reversible system, the entropy is not going to change overall. But the world is not made of reversible processes, it's made of irreversible process. So the delta S of the universe is equal to the delta S of the system plus the delta S of the surroundings. Again, that's the delta S of the universe is the system and the surroundings, right? Combined is always greater than 0. So this right here, I guess I should say this right here is my equation for the second law of thermodynamics, right? For a irreversible process, we know that this is always going to be positive. Delta S is always going to be greater than 0. Entropy is increasing. That's the second law of thermodynamics. What paid the entropy cost? That's the other important thing if something does change, okay? So here we go. Remember, we talked about this. It is spontaneous in one direction, right? So if it's spontaneous in one direction and all of a sudden I reverse it, remember how I said I could put liquid nitrogen on one side and I can reverse it back in the other direction? I'm going from a more ordered to less ordered. It's less ordered because everything is more distributed. More distributed is good, right? So if I distribute this around, the gas is takes up more volume, it is more well distributed, it is higher entropy. So this has an increase in delta S. There's an increase in entropy. That means going back in the other direction is going to be a decrease in delta S. So the question is, what paid the entropy cost? Well, the cost would be whatever took the liquid nitrogen in order to freeze the one side and then close the stopcock, right? So again, the entropy of the universe is increasing, the entropy of the system might be decreasing, okay? All right, so the second law can be generalized. The entropy of the universe is increased in spontaneous process. So Boltzmann came up with this concept of microstates. So S is equal to K log W, capital W. We're going to focus on this idea of W, which is the number of microstates. He basically said, all right, well, let's look at things at a molecular level, right? He basically said, let's just look at entropy at the molecular level. We have a bunch of stuff going on at the molecular level. Thermodynamics principles were developed at this time. And he says, all right, temperature is a measure of average kinetic energy and it's the motion of molecules, and molecules have a bunch of different motions. And this is actually important. You would use this in the future, but there are 3 motions that a molecule can have. It can be translational. Translational energy is a water molecule, for example, traveling, moving left, right, up, down, back, forward, basically any direction a thing moving is translational energy. Simple enough. There's also vibrational energy. Vibrational energy, these are 3 vibrations that we see. So if you have bond lengths getting longer, one length getting shorter, one getting shorter, this scissoring effort where they're kind of wagging in and out. So there's a bunch of different shapes. That's vibrational movement. So lengthening bonds, wiggling of the bonds. And then finally, the smallest one, but rotational energy. So those are the 3 different the types of energy. Okay, so those are the types of energy that we have. So what Boltzmann said is we have these molecules that have all these different motions. So if we take a snapshot in time, right? So if we just take this snapshot of all molecule states, that is equal to microstate. So this microstate is kind of the position that everything is in. So that sampling is a microstate. And then take another moment, we are in another microstate because we have a bunch of things in the different positions. Okay, so what he said is, well, entropy is the measure. So if entropy is a measure of K natural log of log, actually, right? Log of capital W, and K is the Boltzmann constant, which is actually really important constant, but we're going to ignore it for now. The Boltzmann distribution or Boltzmann constant, 1.38. By the way, that's something that I wish I understood better back when I was learning this stuff. Joule Kelvin, okay, the Boltzmann constant. He basically said the number of microstates. So if I increase the number of states or the value of W, I'm increasing the amount of entropy that I have. So the more states it can be in, the higher the S. Great, okay, so that's good. That means that if I look at the delta S, a delta S is just simply K times log W final over W initial. So the difference of those 2, initial and final, is going to give us some values. None of that really matters. Ultimately, a microstate is just the number of positions you can have. So let's just imagine. So if we just took a pause for 1 second and imagined, okay, I have a classroom with 5 seats. Keep it really simple. And I have 3 students. They can sit in 3 different chairs. There are a bunch of different positions I could say. All right, well, student 1 could say here, 2, and 3. So these are like molecules taking up positions. Or I could put them in, 1 here, 2 here, 3 here. So we could just mix them up. So you could think about the number of possible positions that these things can be in. Those are each an individual microstate. And then I said, all right, well, I've got those 3 students still, and I double the volume, or I double the number of seats. There are twice as many, or at least there's plenty more microstates that I have now, right? Or if I increase the number of students, that increases the number of positions that we can have. And so things get really complicated, but ultimately it comes down to this. When I'm looking at increasing in entropy, there's a couple of ways I can do it. So we tend to see entropy increases with an increase in. So increasing in temperature equals an increase in entropy because things get moving faster. Moving faster is more random, higher energy. Increasing temperature equals increasing in entropy. Increasing in volume. More volume that I have, the more positions that they can be in, the more well distributed they can be, we see an increase in entropy. If I increase in the number of molecules, we're seeing an increase in entropy. So all of these things are increases in entropy. And the last thing that I want to talk about is, this is kind of 3A, is yes, we have number of molecules, but also the complexity of molecules. So increasing the complexity of a molecule. So if I look at something like CO2, so there's a couple of different types of positions, like this can shorten as well, or they can both lengthen, or they can both, so there's not too much that CO can do, other than there's a couple of different motions that it can have. But if I increase it to carbonate, all of a sudden we now have, yes, these things can get shorter and longer, but they can also start to waggle. You start to get these other types of shapes as well. So the more complexity, the more degrees of freedom, that's the term that we use for this, equals more complexity equals more randomness. Okay, so that's another thing that we can kind of add to the list in terms of complexity. Okay, and then the final thing is physical states. This one is kind of the standard: solid to liquid to gas. Going from solid to liquid to gas, we've already said this all equals an increase in entropy. Okay, so for each of these, in general, the following are all increases in entropy. Okay, so in general, when a solid is dissolved in a solvent, so we're going from some solid dissolving in a solvent, this is an increase in entropy. If we see a phase change, again, from solid to liquid to gas, that is, in this case, going from, gases are formed from solids and liquids. So gases form from liquids or solids. That is going to be an increase in entropy. Liquids are formed from solids, entropy is increased. That's kind of similar to the first one. The number of gas molecule increases, entropy increases, right? So if I go from N2O4 gas to 2NO2 gas, I've doubled the number of molecules, I've increased the entropy, increases the randomness, increases the number of moles. So I have C3H8 gas, so propane plus 5 oxygens gas yields 3 CO2s plus 4 H2Os. That is also an increase in entropy. So we see all of these different things that cause increases in entropy. So for all of these, I want you to predict, does entropy increase, decrease, or remain the same? So do those, we're going to work on those in class. Same question here. Circle these. I don't think I have a, circle the one with higher entropy. Which one has higher entropy out of these two different states that we have? Okay. All right, good. So this moves us on to the third law of thermodynamics. And I think we're getting down. Perfect. Yeah, so 2 pages left here. So the third law of thermodynamics. So the third law of thermodynamics is also based on entropy. So the entropy of a perfect crystal, or a pure crystalline substance, so a perfect crystal at absolute zero is 0. Okay, so entropy S equals 0 at T equals 0 Kelvin. The idea of absolute zero is basically saying there is no molecular motion whatsoever. No molecular motion indicates we only have one microstate, right? So there's no molecular motion. And that means we have one microstate. Having one microstate indicates that, well, our entropy is pretty much 0 because there is no disorder. But as soon as we increase the temperature just a little bit, we have disorder and we have n number of microstates. So we've increased it just a little bit and we have entropy. So that brings us to this graph right here, which kind of brings it all together. What we notice on this graph, a couple of things. So first of all, what you notice is entropy starts at 0. So at 0 Kelvin, S is equal to 0, as we would expect it, because it's perfectly, there's only one microstate, there's only one position. As temperature increases, we see an increase in entropy. When we have an isotherm, right? So this is an isothermal right here, an isotherm, iso, just single temperature. When we have an isotherm, okay, phase changes are isothermal, but entropy is still increasing, right? Although the temperature is not changing, we know we're going from solid to gas or liquid to gas, or solid to liquid, and then liquid to gas, okay? And then the last thing is what we're gonna notice is becoming a gas, which is a much, much greater entropy because we no longer have those intermolecular forces. The delta S of melting or fusion is going to be less than the delta S of boiling. Okay, so we're seeing a much bigger change in entropy as to be expected when we're going to that highest state of matter, which is gas. Okay, all right, great. So let's actually put some numbers to all of this and some ideas. So standard molar entropies. So first of all, a standard molar entropy, we know an entropy is measured in joules per Kelvin, joule per, but a molar standard entropy, we got to include an amount there, the molar part. So entropy is in joule per Kelvin, but a standard molar enthalpy is joules per mole Kelvin, okay? Standard entropies tend to increase with molar mass. And the larger, more complex molecules, again, for reasons, tend to have increase in entropy. Notice the entropy here versus entropy of methane, we see an increase. We can't predict what those numbers are. We can just predict whether it's increasing or decreasing. So if we take a look at this, we notice these entropy values for solids versus these entropy values for liquids. Yeah, they're pretty much increasing, but we can't be too certain because notice that these complex molecules, because we have four ions for iron chloride or 2 ions for sodium chloride, actually has less entropy than liquid water, weirdly enough, okay? But we can also notice that the general trend is lower, higher, and even higher as gases. So we do see those trends looking at those things and looking at, you know, hydrogen versus nitrogen. Nitrogen is heavier, it's got more entropy than the hydrogen does, okay? Yeah. And oxygen, again, greater than that. And once you get increased complexity, again, mass is going to play the major role there. Although it's more complex, it actually still has less entropy because mass plays a huge role in it. So increasing standard entropy. So you're always going to be able to look these up though. So entropy changes can be determined because we actually have those values, and now we actually will do a lab so we can determine what those are. So delta S, much like enthalpy, we already did this with enthalpy, is the summation of moles of those S values. I should say S naught, it's not delta S, by the way. Standard of the products minus the summation of your moles times the entropy, standard enthalpies of reactants. Okay, so there we go. We've already done these types of calculations. So calculate the change in entropy of the system, delta S, for the synthesis of ammonia. And so I'm going to write out the synthesis of ammonia for you. N2 gas plus 3H2 gas yields 2 NH3 gas. There we go. And of course, we're going to create our little table, moles and S naught values. So 1, 3, and 2. And you can plug these in. So 191.5. H2 was, it's over here, the table to the left. You can find these in the appendix, by the way, if you need to. 130.6 and 192.5. What is your overall delta S? Do that calculation. Again, summation of products minus reactants. Your delta S should come out to be negative 198 joule kelvins. Yeah, so do that calculation. Hopefully that's what you get. If you don't, come talk to me. And then we are going to talk about entropy changes Yeah, so this is the last page. So remember that, again, delta S of the universe equals delta S of the system plus delta S of the surroundings, okay? And we know that during an isothermal process, delta S of the system is equal to Q of the system all over temperature. That means that the delta S of the surroundings is going to equal negative Q of the system all over temperature, okay? So the term universe, again, for a spontaneous process, that's true, but the delta S of the universe we know is greater than 0. Again, this is the second law of thermodynamics, okay? So we have this new state function. I'm just going to write it out. You can look through this if you want to. Ultimately, this is called the Gibbs free energy, and this is going to be the most important equation that we have for the rest of this chapter. Delta G is equal to delta H minus T delta S. We can determine if things are going to be spontaneous based on this equation. So the Gibbs free energy is going to tell us that. It's based on the enthalpy and the entropy. So the randomness is important as well as the energy involved, but this is the Gibbs free energy that we're going to focus on. And that's why we're going to care. So we're going to start with this next time.